The characteristic equation method is a method that is used for finding solutions to a specific class of homogeneous second-order linear ODEs. To be more specific, consider the class of homogeneous second-order linear ODEs where the functions p of t and q of t are simply constant functions, namely, consider the ODE as you can see it here, where x is the unknown, and you can see that capital P and capital Q are representing two constants. In general, these constants can be complex numbers, however, let us assume they are real. The method consists in writing a guess solution of the form x of t is equal to the exponential of lambda times t, where lambda is a constant to be determined. We cannot assume that lambda is real in general, so let us allow for lambda to be complex, but it is always a constant. Now, given this guess solution, we can calculate its derivatives. As you can see, each time we take a derivative of the exponential, a factor lambda appears. However, the time dependence of x of t, x prime of t, and x double prime of t is always of the form exponential of lambda t times a constant. So the ODE for x reads as follows. The combination of x double prime, x prime, and x has to be equal to 0 for all t real. But we can factorize this latter equation by the common factor x of lambda t, obtaining this, and finally noting that the exponential of lambda t is different from 0 for any lambda and any t, we can divide by it to obtain this equation, which is a simple quadratic equation for lambda with roots given by this formula. So we have two roots, lambda plus and lambda minus. In the generic case, where the discriminant p squared minus 4q is different from 0, we see that lambda plus is different from lambda minus. So you have two different roots in the generic case. We will leave the degenerate case when p squared is equal to 4q to another video. So in the generic case, when the discriminant is different from 0, you get two different roots of the quadratic, so each root gives you a different solution of the ODE. x1 of t equals exponential of lambda minus times t, and x2 of t equals exponential of lambda plus times t. These two solutions can be shown to be a set of fundamental solutions on any interval, in particular on the real line. So we propose the following exercise to finish this video. Calculate the Wronskian between the two functions x1 and x2 defined above in terms of p, q, and t. You can pause the video now if you want to solve this for yourself, and once you're ready, go to the next part of the video. So here is the answer. First, by definition, the Wronskian between x1 and x2 is equal to x1 times x2 prime minus x2 times x1 prime. Replacing our functions in terms of t and lambda, the first term gives us e to the lambda plus times e to the lambda minus times t multiplied by lambda plus multiplied by e to the lambda plus times t. The next term is equal to minus e to the lambda plus times t multiplied by lambda minus multiplied by e to the lambda minus times t. This can be further simplified by noting that the product of two exponentials is the exponential of the sum of the exponent, leading to this. And now we can notice that there is a common factor, so we can factorize. Finally, we need to write these lambdas combinations in terms of p and q. From the formulas for the roots, it is trivial to show that the difference lambda plus minus lambda minus is equal to the square root of the discriminant, and the sum of the two roots, lambda plus lambda minus, is equal to minus p. So this is the final result for the Wronskian in terms of p, q, and t. Notice that once you have found explicit formula for the Wronskian, you can use definition 6 in the notes to conclude that the functions x1 and x2 are a set of fundamental solutions on any interval. Thank you for your attention.